So week 8 precept, we're going to talk about the graph algorithms, and I'm going to go over the 1A and 1B again. So for example, we look at DFS demo. Essentially, what we have is a graph, and we want to kind of do DFS on this graph. I'm going to adopt a sort of a color scheme to show that we perform DFS using a stack. And if things are on the stack, I'm going to color them with this color, and if they are processed, I will color them with blue. Otherwise, if it's not in the stack or processed, I will color them with nothing. Right. So if you start with 0, so essentially put the 0 in the stack, then 1 in the stack, 4 in the stack, 5 in the stack. So after the first sort of round, you're going to see your graph like that. Now, in the second one, now because we can't go any further, we're going to pop 5 and print that to be the first one, then pop 4 and print that to be the second one. And now we're back in 1, and then from 1 we can put more things into the stack. We're going to put 6 and then 3. So now these are in the stack, these are already being processed. So the next one, we're going to process 3 and 4 because we can't go anymore. So we process 3, then we process 6, and then we backtrack to 1. So at 1, we cannot go anymore. These have been processed, so we're going to process 1, and then we backtrack to 0. From 0, you can create a new path, 0 to 8, 7. They are all in the stack now, and then we will pop them from the stack in that order, 7, 8, 2. Once it's all done, then we have the 0 there. So the numbers marked here are the numbers that it's going to be DFS is going to produce that sequence. All right, so let's go to the next demo, which is the BFS demo, where we have we want to do BFS, breadth first search. So we're going to put the 0 in the queue. So here we use a queue, and then we put its neighbors into the queue. We dequeue 0, put the neighbors into the queue. So these are in the queue. Now, we will mark them in the order they go into the queue. So this will be 2 because they have the low index. There will be 3. This will be 4. So in our BFS, they will come out in that order, 0, 1, 2, 6. So the next thing we're going to do is to dequeue 2 from the queue, and then put the neighbors into the queue, and then use the next number for that. This is the 5th element that will be processed. And then we will dequeue the next one in the queue, which is 2, and then it put its neighbors into the queue, which is 8, and that will number 6, and then dequeue 6, and then put its neighbors into the queue that are not processed. That'll be 3, and then the next thing to dequeue would be the one with the lowest number, which is 5. So we take that, and then we put the neighbors into the queue. That becomes 8, and now we process the next number 6, and then the next number 7, next number 8, next number 9, and that's how the BFS would work. So it gives you what vertices we can reach from a given vertex. All right. So let's have a discussion about question number 2. In the question number 2, we are given this piece of code on the undirected graphs. So this is an undirected graph. And the first question is, what is the purpose of this method? So let's just go over the code a little bit. So in the foo method, you have a graph given and sort of a source vertex given. So we create a new queue. And then for all the vertices, we initialize 2 arrays. One is distance to v, and we have another array called marked v, false. That means this distance to array will contain distances from S to every other vertex in the graph. So we assume that to be the max value, and then we will try to update that as we go. And initially, nothing is marked. So the way we start is that we know from distance from S to S is 0, and S will be processed to be true. Now we enqueue S into the queue, and while queue is not empty, we dequeue S V, and then we find the adjacency elements of those things, and if they're not marked, we add there's an edge to W coming from V, because notice that the V is the source vertex and W are the adjacency vertices from that. So we know there's an edge from V to W. That's what this says. And then the distance to W would be one more than distance to V. So if I know the distance to V, so if I'm going from S to W through V, if I already know the distance to V, then I can just add 1 to get the distance to W. And then once I process an element vertex, I'm going to mark them to be true, and then add them to the queue. So the answer to the first question is that it is a sort of a breadth first search kind of a thing. The purpose of the method is to really go through the code and find the distances to from a source vertex to all the other vertices. So what's the purpose of the code marked in line 1? We actually covered that a little bit. So in some case, what we're saying is that if you're going from S to W, the through V, then the distance is going to be updated based on the distance to W. So for example, distance to S would be 0. So if anyone is directly connected to S, then all of those entries will have distance 1. So essentially we're doing the breadth first search. What if the mark array is not updated? That means suppose that we remove this line. Now that's a problem. So suppose we have an undirected graph with cycles, and we can keep updating because the array will never be marked. So the vertex will not be marked. So you'll continue to increase the distance, and at that point distance is going to go to infinity. So it's not a good idea to remove this. Now let's also have a short discussion about what if this is a directed graph. Suppose it's a directed graph. So I'll ask the question, what if you remove mark W equals true? So if it's a directed graph and it has if it has cycles and it's a directed graph, then but still this is going to go to infinity. But think about this. If it's a directed graph and has no cycles, it's a directed acyclic graph, then if you remove this, what the program will do is to find the longest path from S to a given node. So in some sense, this can work really well if this is a directed graph because we're finding the longest path. Let's say, for example, you're trying to buy an airline ticket by using as many transition points as possible to minimize the cost. That might be an interesting problem. But if it's an undirected graph, in any case, whether the graph has a cycle or not, this is going to lead to infinite loop, infinite distances. So then the final question is, what is the order of growth for V plus E? So the order of growth, we can count how many times this will be done. So let's talk about the order of growth rather than the exact number of things that we do. So obviously this loop is going to be processed V times. So that's whatever you process 2 statements, but overall it's V times. This statement, because we know that every element can only be in the queue once, this only runs V times. Inside, we find all the adjacency elements to that V for each V that in the queue. That means if you do the total for all the V's, you're going to get E edges into that. So essentially, this combination of loops will run V plus E times. So the answer to that would be V plus E for that final part. These are important for you to think. All right, so the question number 3 is about shortest common ancestor, which is really the assignment that you're working on. In a directed graph, a vertex is X is an ancestor of V. There's a path from V to X. So you can kind of draw a picture that in a directed graph. So for instance, let's see whether we can find something here. Yeah. So in a directed graph, that 7 is an ancestor of 1, 2 is an ancestor of 1, 3 is an ancestor of 2, and so on. And so we are describing ancestor. There's a directed path, so it's a path. So that means given 1, 2 and 3 and 5 and 7 are all ancestors of 1. And so the question is asking, in the first place, is the following digraph a DAG? By looking at it, we know that it doesn't have cycles and it's a directed graph. Therefore, the answer to that question is yes. If so, is it a rooted DAG? Rooted DAG means there's one single node with the out degree 0. If you look at this 7, you'll notice that the out degree, that means number of edges going out of 7, is 0. So therefore, there is a vertex with out degree 0. Are there other vertices without degree 0? I guess not. If you look at 6, the out degree is 1. If you look at 0, out degree is 1. Out degree is actually 2 for 0. For 1, the out degree is 2. For 2, out degree is 1. 3, the out degree is 2. 5, the out degree is 1. So 7 is the only one with the out degree 0. So this is a rooted DAG. It's a DAG and it's a rooted DAG. Now, what's an algorithm to identify a rooted DAG? Well, you can think of the adjacency list. All you have to do is go through the adjacency list and find the out degree of every list, and then find out if there's one with a 0. In some ways, you can optimize the code by saying, just go through the adjacency list and look for a single node with no list. That means there's null from that list. It has no list going out of that. So that can be easier to do. You can do that in V time if you do that. So you're looking for the out degree. You're looking for a node with out degree 0, and that can be determined from the adjacency list in the if you determine all the out degrees, that's V plus E, because you have to go through all the vertices and all the edges. And if you just worry about the very specific case, like, okay, I want to find only the out degree 0 vertices, then all you have to do is just go through the entire list and see which ones are empty list, and then check whether there's only one of them at the end. So that can be done in V time as an optimization. Okay, so the next the next part is here, that the part B is that we're trying to find the common ancestor of vertices 1 and 4. So one algorithm we can use is that we do DFS, depth first search from 1. So we create the list of reachable vertices from 1. So they're 1, 2, 3, 5, 7. And from 4, you do the same thing. You create a list of searchable vertices from 4. So we know we can go to 5 and 7. And so we know that reachable vertices from 1 and 4 include both 5 and 7. Now, so the shortest common ancestor would be the one that minimizes it. Obviously, in this case, it would be 7. 7 has a path length of 3 because that's 1 here, and then there's 2 here. So this 2 plus 1, that's the 7 is the one, not the 5, because 5 has a path length of 3 plus 1, which is 4, and 7 has a total path length of 3. So that's part B. So in part C, we want to describe an algorithm for calculating the shortest common ancestor of two vertices in a rooted DAG. So let's assume we have a rooted DAG and we want to run this in at most V plus E time. So that would indicate you would use some sort of a breadth first search kind of an algorithm to do it. You can do breadth first search in V plus E. So let's think of a sort of a common algorithm for doing something like that. Let's assume that we run breadth first search on 1, and we can get the distances to everything that it finds in its breadth first search. So if you get the breadth first search, you will find the distance from 1 to 2 is 1, 3 is 2, 5 is 3, 7 is 4. Actually, no, it would find that the distance to 7 is 1, 2 is 1, 3 is 2, 5 is 3. So if you do breadth first search from these three vertices, you process 2 and 7, they are both 1. They're like, this is like 2 distance from 1. It's like 3 distance. So we have a list of distances as to all the vertices that we can reach from 1. From 4, we do the same thing. So all the vertices we can reach from 4, this would be 1, this would be 2. So we have a list of distances from 4 to every vertex that it can reach. Now, since we know 5 and 7 are both reached from 1 and 4, now because we have distances from 1 and distances from 4, we can figure out which one gives you, which vertex gives you the shortest distance. So that could be one of the algorithms you can use. You can run in B plus C because you're running breadth first search to do that. Okay, there are a lot of other solutions. The correct solution must use DFBFS. You can come up with a lot of different solutions that may not work. There are other solutions you may want to think about, like for example, you can say, well, let's run BFS from one of the two starting vertices, then run the BFS from the other vertex, and return the first vertex, which you see, which is already marked. That can be misleading because you don't know whether the first one is the one that's going to give you the correct one. In the count example below, we're looking for the SCA of 1 and 4. First, we do a BFS from 1. So we reach these vertices, then we do a BFS from 4. We reach these vertices. But we know that 7 is visited before 2, so 7 is only flagged as the SCA. But the correct answer would be 2. So it's not a good idea to, in the second one, so that you have to run the BFS from one vertex first. But in the second one, you shouldn't stop when you see the first common ancestor, because that may not be the correct answer. So you've got to be careful there. And then the next part of the of the precept is talking about this idea where you want to do the shortest ancestral path from two vertices, two sets of vertices. So A that contains 3 and 10, B that contains 9, 15, and 12. So what you want to do is to find the BFS from these nodes to all of these things and find the shortest one. So you consider this as a set of things. So you find the minimum from any one of these sets to be the one that's going to work. Right, so an algorithm could be that you could put these things into a queue and run the BFS and mark the keep the short distances, like you could put 3 and 10 and run BFS from 3, mark the distances as to each of the things that you can reach, run the BFS from 10, mark the distance to each one, update it if you find a shorter distance, and then eventually you can find the distance, the shortest distance from this set, 3, 10 to that. The same thing with this one here. And there's an easier way to think about this. Another way to think about this, in fact, is to really think about a sort of a, if you recall percolation assignment, in the percolation assignment, we had the first row represented by a virtual node. So same thing, you can do that, so you can take a set and add another node and say, okay, let me connect that node to each one of these things. So I'll add another node and connect to 3 and 10. So essentially this node represents the entire set here. And then I will do the same thing for this one here. So I'll add another node and create edges to each one. And so now the problem reduces to running from one vertex into another vertex, finding the shortest common ancestor. All right, so next I'll talk about the assignment. So finally, let's go with the assignment. The assignment is about Wordnet, which is a very important, interesting project from Princeton. Essentially, that the idea would be that given there's a relationship, jump is an increase or jump is a descent. So all these things, these are called synsets. So there are synsets. So synsets can contain more than one noun. So these are nouns in the synsets. And these synsets has some index, and that index becomes the vertex of a directed rooted DAG. So essentially, you're dealing with a rooted DAG in this case. So you want to come up with a algorithm that will do interesting things like find the shortest distance between, say, jump and transgression. So you'll have to figure out what the most common ancestor is. So sort of like, if you come from here, this one here, from here, you can get to that. So you can find the shortest common ancestor. Um, so there are a few things that are really important to you. For example, your synset file is given as a number of IDs separated by a comma and a bunch of nouns, that's called a synset, and the meaning, which you can ignore. And so what you need to do is read this file, uh, tokenize it by the comma first, and then tokenize it by this. So tokenize by the comma, and then tokenize by the space to get the nouns. So essentially, as you read this, you can build a map between the IDs and the nouns for that ID. So you have one map where you have a keys, the ID, and then the nouns and so on. And then you probably need another map to know a given noun can be in multiple synsets. So for instance, if you look at here, jump is in this ID, this synset, and also in this synset here. So if you given a noun can be in multiple IDs. So therefore you have to have a map that will tell you, given a noun like jump, what synsets is the noun in. So I suggest that you think of a way to come up with some data structures to build those two relationships in a more efficient way, log n or better. Then once you do that, you process your graph. This is your director graph. There's an H from 34 to that, 34 to this, and so on. So you process that, and you build the director graph. So there's a class called digraph, which you can use to build this director graph. So then you try to create, you try to complete this Wordnet API. So for instance, given a word, is it a noun? Well, if you can have a way to know what nouns are in here. So for example, if you have a noun as a key, and then you have a synset, a bunch of synsets associated with that, then you can check whether that noun exists. And then you want to find the shortest common ancestor of noun 1 and noun 2. So suppose noun 1 is jump. So what you need to do is you go here and say, okay, well, jump is in this synset and this synset. So there are two IDs for jump. So that's a set of IDs. And then you find the set of IDs for noun 2. So noun 2 may have one or more IDs. If it's a valid noun, it must be in the thing. So essentially, once you are given noun 1 and noun 2, you got to find out what synsets these noun 1 and noun 2 are. So it gives you two sets of IDs. And then you find the SCA from those two sets. All right. And then also you can do the distance. There are a few things that I like you to pay attention to. So first of all, when you try to find the when you're working on this, there are a few things that can be helpful in doing things. So for instance, that there are a number of files that can be helpful. Okay, for instance, that if you go to checklist, there's a digraph. What was that? Okay, so go to checklist. There's a directed somewhere here is a directed. So in other words, when you want to find do the BFS, you don't have to write your own BFS. You can use the methods, Java classes that are in the Ancestor library. If you're looking for whether something has a cycle, you can use Java classes available in the Ancestor library. So you can do all of those things using the existing libraries. All right, so once again, when you do the regular assignment, use the class methods from the class breadth first directed paths. You will find that you can find the breadth first search from a single vertex, methods for that, and also from a set of verses. So you should use that. So don't do the optimization yet. Do this first. So it says if you're going to attempt the optimization or extra credit, you should first implement the classes to use the BFS algorithm that we provide them, which is in the breadth first directed paths. And then you can try to optimize to try to get things. So possible optimizations generally center around the fact that the most of the cost of the regular implementation is that we find a lot of things that may not be useful. So for example, we may compute all these arrays. That's a bottleneck. So if you can avoid that, then it can help you optimize things. For instance, that I think in the assignment spreadsheet, it tells you that if you want to optimize things, then you can, you should only, given two vertices, you should only be looking at the BFS from those two vertices there. So that's an important part of the assignment. You have to write your own methods to do that if you want to get that extra credit. There are a few other things that are important. When you read the hypernyms file, you have the syntax files. You have two files. So when you read the hypernyms, it's the one used to use the dry graph. Consider the dry graph, not the Wordnet. Okay, they have different formats. You want to read the input files once. For example, when you read the syn sets, you may want to know how many things you get. Like for example, in the syn set file here, as you read, you can find out how many IDs are here, and that number is the number of vertices for the next file you have to process. Okay, and then there's also string.split, which will be useful for splitting strings. And also you may fail a timing test if you do not construct the SEA object in the constructor. So make sure that the SEA object is constructed in the constructor, but not in these classes, SEA or distance, because that can be called many times. So that's basically it. And if you have any other questions, you can email or post to Piazza. Good luck.